summation n is equals to 1 to infinity 3 upon n plus under root n. So this is our second example. Now for that second example, here we have an is equals to 3 upon n plus square root n. Now we know that 3n is equals to n plus n, that is 3n. Now that is greater than, strictly greater than n plus square root n, because here we have n greater than 1. So square root of n will be less than that value n, and the last term will be n greater than 0. Now this term, from these things we have 3n as a greater than n plus square root n, and that implies 3 upon n plus square root n is greater than 1 upon n. Now this thing here we have as a an greater than, this called this 1 upon n series as a dn. Now we know that summation 1 upon n is equals to summation 1 upon n raised to p with p is equals to 1. So by p series we get p is equals to 1, and so summation 1 upon n diverges by p test, right? So here we get a series as a divergent series summation dn, and an is greater than dn for every n greater than or equals to 1. So by comparison test, summation an, that is summation 3 upon n plus square root n as a divergent series diverges. So this second example is a divergent series. Now let us take the third one. Third example is that summation n is equals to 1 to infinity n upon 3n plus 1 whole raised to n. Now in this example, here what we have is a an is equals to n upon 3n plus 1 whole raised to n. Now that term is less than n upon 3n whole raised to n, because the reason is that 1 upon 3n plus 1 is less than 1 upon 3n, because the denominator is greater than. Now n upon 3n raised to n is nothing but 1 upon 3 raised to n, and that series called as a Cn. Then summation Cn is convergent series, because we have ratio r is equals to 1 by 3 and a is equals to 1 in geometric series. Right. So here we have an is less than or equals to Cn for every n greater than or equals to 1, and summation Cn as a convergent series. So summation an converges by comparison test, right? So these are the examples for comparison test. Now let us see the next result, that is for again a positive term series, and that result is nothing but a limit comparison test. Now limit comparison test says that if an and bn both are positive for some finite for all integers n greater than or equals to some finite integer n, and if we have limit n tends to infinity an upon bn is equals to c, where c is greater than 0, here we have to observe that c is always a positive, so we can write down that c is not equals to 0, then summation an and summation both are converges or both are diverges. That means both are converges series or diverges series simultaneously. It may not happen that one is a convergent and another one is a divergent series. Now the second result says that limit n tends to infinity an upon bn is equals to 0, then bn is a divergent series, bn is a convergent series, then an is a convergent series, and another last result says that if limit an upon bn is equals to infinity, then and bn is a divergent series, then summation an diverges. That means last two results says that if that limit is 0, then denominator series is convergent, then numerator converges, and if that limit is equals to infinity, then denominator diverges, then numerator diverges. Now let us see some examples of that limit comparison test in telecom. So the first example for limit comparison test is that summation n is equals to 1 to infinity 10 n plus 1 upon n plus 1 n plus 2. So this is our first example. Now here what we have, an is equals to 10 n plus 1 upon n times n plus 1 n plus 2. So this is our an. Now from this an we want to find out bn, and for that what we have to do, take a highest power of n common from numerator as well as n from denominator. So from the numerator highest power of n will be 1, so here we get n times 10 plus 1 upon n divided by, now n is already there, now from n plus 1 take n common, and same for n plus 2, so finally we get n cube, and inner terms will be 1 plus 1 upon n and 1 plus 2 upon n. Now n upon n cube will be cancelled out, n, and the final term will be 1 upon n square. So consider that bn, or take bn is equals to 1 upon n square. Now limit n tends to infinity, an upon bn is equals to, an will be 1 upon n square into 10 plus 1 upon n divided by 1 plus 1 upon n, 1 plus 2 upon n divided by bn, that is nothing but 1 upon n square. So 1 upon n square, 1 upon n square will be cancelled out, and here we have limit n tends to infinity. Now limit n tends to infinity, 10 plus 1 upon n divided by 1 plus 1 upon n, 1 plus 2 upon n. So this is our final term. Now when we take n tends to infinity, 1 upon n will goes to 0, so in the numerator we get only 10, and in denominator 1 plus 0, 1 plus 0, that is 1 into 1, 1 into 1 is 1, so as a final limit we get 10, which is not equals to 0. That means by limit comparison test, summation an and summation bn both converges or diverges simultaneously, but by p-test, summation 1 upon n square converges, because here we have converges because we have p is equals to 2 and which is greater than 1, and so summation an converges. So this is a first example by using limit comparison test. Now let us take the second example. Summation n is equals to, second example, summation n is equals to 1 to infinity sine 1 upon n. Right. Now in this example here we have an is equals to sine 1 upon n. So an is sine 1 upon n, and for that what we have to do, here we consider bn is equals to 1 upon n. Bn is equals to 1 upon n. Now calculate limit n tends to infinity an upon bn, that is equals to limit n tends to infinity an upon bn is nothing but sine 1 upon n divided by 1 upon n, and that limit is going to be 1 because we have one result that limit theta tends to 0 sine theta upon theta is equals to 1. Now here we have limit as a theta tends to 0, and in this term we have n tends to infinity, but if we observe the terms, then here this term is going to be 0 and denominator is also going to be 0, so that two results are same if we choose 1 upon n is equals to theta. So that limit is equals to 1, n is not equals to 0. So by limit comparison test, summation an and summation bn converges or diverges simultaneously, right? But again by p test, summation 1 upon n is diverges because we have p is equals to 1, and so summation an diverges, right? So this example says that sine 1 upon n is a divergent series. Now third example is summation n is equals to 1 to infinity ln n whole square divided by n cube. So here what we have as a an is ln n square upon n cube. Now take bn is equals to 1 upon n square. Bn is equals to 1 upon n square. Then calculate limit n tends to infinity an upon bn, that is equals to limit n tends to infinity an is nothing but ln n whole square divided by n cube and upon bn, so numerator will be n square by 1. Now n square and cube n square will be cancelled out, and we get that limit as a limit n tends to infinity ln n whole square by n. So if we take n tends to infinity, ln n, that means logarithm is an increasing function, and therefore it will goes to infinity, and therefore its square is also goes to infinity, and denominator is also goes to infinity. So this is indeterminate form of the type infinity upon infinity. Now in such a case we have to use Lapital rule, and Lapital rule says that the differentiate the numerator as well as the denominator, and that is nothing but limit n tends to infinity derivative of n square with respect to n will be twice ln n into the derivative of ln n, that is log n is 1 upon n, and the derivative of n is 1. So here we get a final limit as a limit n tends to infinity 2 ln n upon n. Now again this form is of the type infinity upon infinity form, indeterminate form, and so again we have to use the limit comparison test, Lapital rule, and that is nothing but limit n tends to infinity twice derivative of ln n is nothing but 1 upon n and is 1 by n. Now when we take n tends to infinity, this term will be goes to 0, so we get limit n tends to infinity an upon bn is equals to 0. An upon bn is equals to 0. So by limit comparison test, if we have summation bn as a convergent series, then summation an converges. So denominator series is converged, then summation an, that is numerator series, will converge. But by p-test, summation bn, that is nothing but summation 1 upon n square, converges, and so summation an converges by limit comparison test. So here the limit comparison, second result of limit comparison test is used. That is, if we have limit n tends to infinity, an upon bn is equals to 0, then and bn converges, then summation an converges. So we have to use the second portion. Now let us go for the third one, that is fourth example, summation n is equals to 1 to infinity 1 upon ln n whole square. Now in this series, what we do, here we have an is equals to 1 upon ln n whole square. Now take bn is equals to 1 upon n. Bn is equals to 1 upon n. Then limit n tends to infinity, an upon bn is going to be limit n tends to infinity ln upon bn, an upon bn, an is 1 upon ln n whole square and bn is 1 upon n. So numerator of numerator will be denominator, so we get here n upon ln n whole square, right. Now if we take n tends to infinity, n upon ln n square, then this term is going to be of the form infinity upon infinity, again indeterminate form, and by using Lapital rule we get that limit as the limit n tends to infinity, n derivative of n is 1 and derivative of ln n square is nothing but twice ln n into 1 upon n. 1 upon n will be in numerator, so again we have 1 into n as a n and denominator is equals to twice ln n. When we take n tends to infinity, again this is of the form infinity upon infinity, and so this term will goes to derivative of n is equals to 1 upon 2 into 1 and 1 by n. 1 by n is in denominator of denominator, so it will be in numerator, and this is equals to nothing but infinity. So here what we have, limit n tends to infinity